up next we have a twice differentiable function. We're given what happens in terms of the function value at 8, the derivative at 8, and the double derivative, or the second derivative at 8. The question is, what is occurring at h at the point 8, 5? So the idea there is, well, the first derivative is equal to 0, which means we have some kind of critical point. Now again, a critical point is where the first derivative is 0, so we're either looking at something like this, or we're looking at something like this, which means we're either looking at a local max or a local min, and the question is, which is it? And we need to look at the second derivative, because the second derivative is negative. And the second derivative says what's happening at your function around that point is going to be concave down. So this one is concave down, which means what we're looking at is essentially at the x value 8, we have the y value 5, and we have a local max. Again, that's because the second derivative is telling us our graph is concave down, but our first derivative is 0. Let's see here. Remember that some of these can get a little wacky in their answers in terms of what they tell you, so just kind of be careful about assuming what it is. For instance, if h prime was not equal to 0, we couldn't tell if this is a minimum or a maximum, so just kind of be aware of that. All right, up next, we're supposed to select all intervals where g prime is greater than 0 and g double prime is greater than 0. And what that means is we're essentially choosing where this graph is increasing. And so let's just kind of think about that first. It's increasing up until you get to -3, then it decreases, so we don't care about that. So far this is the first sliver we care about, and then also from here onward. So these two slivers are where the graph is increasing, so that satisfies the first condition. The second condition is where is it concave up, and this sliver would be concave down. So ignore this, the only answer is this interval right here. So we have to contain everything that is kind of going on here. 1 and 2 is definitely within that part, and also 2 to 4 is within that part. So be careful that you check all that apply. All right, up next, we have to do some calculus-based justifications for the fact that f is decreasing, and the reason f is decreasing based on this chart here is because f prime is negative. Remember, calculus means read derivatives, talk about derivatives, because all of calculus really comes down to derivatives and integrals. So if your derivative is negative, then your function is decreasing. All right. Oh no, a word problem. Rita attempts to write a formal justification that g prime of x equals 0.4 has a solution where x is between -1 and 4. Is her justification complete? Polynomial and trigonometric functions are differentiable continuous at all points in the domain. That is true. Also g -1 and g of 4, -1, 1. And I think, yeah, that means our justification is complete. So this is a mean value theorem question, super important for the AP exam. What the mean value theorem says is as long as your function is differentiable and continuous at all points in your domain of interest, which they did address, and then also if you find the slope y2 minus y1 over x2 minus x1 of your function, then at some point, because it's differentiable and continuous, your derivative must be equal to that as well. So just to give you a picture, again, let me just draw some kind of differentiable and continuous function like this. And if I'm supposed to find the average rate of change from here to here, if those are my endpoints of the interval, like -1 to 4, and it looks like this, that's a bad graph. I was looking at the screen and not the paper, and that really threw me off. If I just directly connect it like that, close enough. The idea is we can actually, based on my drawing here, I can kind of see 2 points probably right here where the slope, gosh, I gotta stop looking at the screen. This point where the slope looks like it would probably be parallel, and also this point. That's what the mean value theorem says. It says if your function's differentiable and continuous, then as long as you try to connect 2 points anywhere, somewhere in between, derivatives also have to, at least one, has to also be identical to the average rate of change, or parallel to the average rate of change. All right. Oh my gosh. Well, this is disgusting. Actually, I remember we did this one in class together once. I miss you all so much. All right, anyways, We're supposed to write the equation of the vertical line that's tangent to the curve. Now the idea is a vertical line has an undefined slope. So where is dy dx, the equation for the slope, undefined? Well, that would happen if x is equal to 0, or if y is equal to -5/2. All right, hopefully you can see that's where the denominator will be 0. Now the question is, which one of these is a valid solution? Notice here, if you plug in x equals 0 into the equation itself, you would end up saying that 0 equals 50, and so that's definitely not true. So again, it's more so not that this is a, how do I say this? This is not a coordinate pair. This is the x value of one coordinate, which evidently doesn't have a solution, and this is the y value of a different coordinate. That's just something to keep in mind. So the question is, where can this be true? So let me plug in -5/2 here into my equation. When I square that, I'll get 25/4, plus if I plug in -5/2 here, I would end up with -25/2 times x equals 50. Now I'm kind of combining my terms here. This is nasty. But this would be -50/4, which means overall I have -25/4x equals 50. And that means x equals, if I multiply that, that's going to be -8, I'm pretty sure. Okay, so we've done a lot of work so far. And you know what I realized? I realized I didn't have to do this much work. Because the vertical line, actually no, I did have to do all this work, never mind. Remember that a vertical line in kind of algebra 1 is going to cross through the x-axis. And the way we write the equation of vertical or horizontal lines is we always write the value based on the axis it crosses. So a vertical line crosses x, so it's x equals something. So I actually did have to go through this whole process. It's x equals -8. So again, you have some crazy curve, and you know the derivative. They wanted the vertical tangent, so we had to find anywhere that this derivative was undefined, in other words, vertical, and then find the only coordinate that satisfied that, and then write the equation of the vertical line, in this case, that it corresponded to. 5 more. Oh my gosh, my least favorite. Well, here it goes. When I look at function 1, I notice that function 1 has 3 critical points, 3 places that the derivative should be 0. And it looks like those 3 places correspond to graph number 3. So in other words, when you look at number 1, number 1's increasing just barely. So you see number 3 is above 0 just for a little bit, then it equals 0, and then it's saying the slope is decreasing up until you get to about -1, and we can see that's true here as well. So hopefully you can see where I'm getting that. So in other words, 1 is going to derive to 3, and now the question is, does 3 derive to 2, or does 2 derive to 1? So let's see here. Does 3 derive to 2? In other words, does 2 only have 1, 2, and barely a third critical point at these locations? And the answer is actually yes. Again, right here at about -3, it changes from decreasing to increasing, decreasing to increasing. And right here, it changes from increasing to decreasing right about at 1, so that's true. And then right here at 4, it changes from decreasing to increasing. It changes from decreasing to increasing. So 1 derives to 3, and 3 derives to 2. Which one is that? A. Oh, I'm so glad I didn't get that wrong. Okay, now I actually have to find the value that does satisfy the mean value theorem for this interval. Again, the mean value theorem is essentially the slope formula in finding where the derivative is equal to the answer of that slope formula. So we need to know y2 minus y1 over x2 minus x1. And, sorry, I'm going to cheat here. Actually, I'll show you some calculator tricks just in case it's been a while. Again, if you have a calculator at home, it's definitely still good to know these. They're going to be writing the FRQs most likely so that people could answer them without a calculator. So maybe that means your calculator won't actually be helpful at all. Maybe it still will be helpful, but remember this wonderful alpha f4. You can call the function you wrote down. So I can actually type it in like this. I want y1 of 6 minus y1 of -3, and that's going to be divided by y minus, or sorry, x2 minus x1, or 6 minus negative 3. And so I get 7. Now the question is, if that's the average rate of change, in other words, think back to that picture I drew before, who knows what this wacky function is, but if that's the average rate of change, where am I going to find at least one derivative in between those two x values, negative 3 and 6, where I get a derivative equal to 7? So let's derive h. It's going to be 3x squared minus 18x plus 7. Now this time we're trying to figure out where this is equal to 7, not equal to 0. Commonly we're asked where does this equal 0, so just be careful about that. Now the thing is, this is actually kind of convenient, because now when I subtract 7 to the other side, I'm still ultimately solving for where something's 0. It just wasn't that initially. We'll do some factoring. And we get two answers. We get positive 6 and we get 0. And the question is, which one of these is, and here's the most important part, in between the interval of interest? And the answer is 0. So we don't take the endpoints, we have to find something in between. All right, how many more questions? Oh, 3. Can I do this in 2 minutes? Where is the graph concave up? Now, I'm not going to be able to do this in 2 minutes because I have to derive this twice, unfortunately. So let's find h prime. Concavity is found by looking at the second derivative. Now, h prime, I got to rewrite this first. I'll just rewrite h of x. That would be negative 27, and then I would write parentheses x minus 6 to the negative 1/3. That's what our function is originally. If we bring up that root, it's a third root, so it's to the 1/3 power, and we're going to make it negative since it was positive in the denominator. So now h prime, we have to do the chain rule here, but luckily the inside derives to 1, so just multiply 1 to everything, so nothing changes. Now we have the negative 27. Now we drop the negative 1/3, and we subtract by 1, which is negative 4/3. And this is really just going to be positive 9, but I'm just going to keep on going for sake of time. Now I'm going to take the second derivative. Again, I have to do the chain rule, so a 1 pops out. I still have the negative 27 before. I still have the negative 1/3 from before. I'll simplify all this stuff in a second. Now I have to multiply a negative 4 over 3, bring that down. Subtract it by 1 again. Now I have negative 7 over 3. And let's see here. The question is, where's this concave up? Let me simplify this here. This whole thing is going to be negative 12 divided by x minus 6 to the 7/3. The important thing about this denominator here is that they're all odd numbers. Now what that means is if you plug in a negative value here, the negative is going to be preserved. So the question is, where will this denominator be negative? And that's going to happen whenever you actually plug in something that is less than 6. And that's the answer. Anything less than 6 will yield a negative answer. Maybe I'll just do all these and I'll speed up the video. You'll hear my voice go fast. All right, same idea. Where does the graph have a point of inflection? So it's time to derive this twice. So we'll find g prime first. Negative 8x cubed plus 24x squared minus 24x. Now I'll derive it a second time. Now it's negative 24x squared. Now it's positive 48x, and now it's negative 24. And if we factor out a negative 24, and we factor in general, you're going to end up writing x minus 1 squared when it's all said and done. So I'm skipping the factoring work there, but hopefully you see how I ended up getting there. And the question is, where does this graph have a point of inflection? And be careful, because an inflection point is not just where the second derivative is 0, it's where the second derivative changes sign. And the key about this one is you're squaring this parentheses, which means this, whatever you plug in, is always either going to be positive or 0. So in other words, this overall g prime is always going to be negative or 0. So it actually never changes from negative to positive, so it never has any inflection point. Last but not least, give the calculus-based justification for why f has a relative maximum at c, relative minimum at c, and that is because f double prime is concave down at c. Sorry, no, I'm losing it. That would be the calculus-based justification. So given that f prime of c is equal to 0, so in other words, they're saying because you know the slope is 0, what also guarantees that since the slope is 0, you're dealing with a relative minimum, and that's the fact that the graph is concave up. And we kind of went over that before. If you have a concave up and you're looking at where the slope is 0, well, you're looking at a local min or a relative min. And there we go. So hopefully your questions are similar, or you can figure them out from this explanation. have